Hello again, and welcome to the last lecture of Biostatistics and Epidemiology. Again, my name is Gabrielle Cahill. Learning objectives for today are to go over the structure of hypothesis testing, to understand how to choose the appropriate statistical test given the data you have and the question you want to answer, and finally, to understand the basics of regression models and what they are. And here is today's lesson plan. I've marked the categorical and continuous test areas with the symbols as we used before in the first lecture. Recall from last week, we discussed the steps to take when you're doing a statistical test. The first thing to do is determine your null hypothesis and the alternative hypothesis. Remember, the null hypothesis is what you will decide to reject or accept based on the result of your statistical test. Then decide on the level of significance. This is the critical value alpha, usually 0.05, that you will compare to the p-value you calculate using your data. Next, select the statistical test you want to use. We will talk a lot more about this today. Then, calculate your test statistic. If you are calculating by hand, determine what the threshold value is for the level of significance you have decided is the critical value, at which you will reject the null hypothesis or not. Finally, draw your conclusion. Will you accept or reject the null hypothesis? And interpret your results. Note that if you use a statistical program, you can skip steps 4 and 5, and instead of comparing your calculated value to a threshold value that corresponds to the level of significance, that critical value that you have chosen, your program will calculate a p-value for you that you can compare directly to your critical value alpha. Again, this is usually 0.05. So what test to use? This depends on the question you want to answer and the type of data you have. Questions that are important to consider are things like, is your data categorical or continuous? Are you comparing your data to a known population value or to another sample? How many other samples? You can use a figure like this to help guide your choice. We will not cover all of these methods, but it can give you an idea of where to start and what tests you might want to investigate further after this course. And here it is, again, just a little bigger, so you can use it as a resource later when choosing what test you want to use. First, we will cover tests for categorical data. The chi-squared test is used when both the variables are categorical in order to compare two or more proportions. The null hypothesis in this case is that proportion 1 is equal to proportion 2. And if you have more than two proportions, equal to proportion 3 and 4, and so on. The assumptions are that the samples are random, the observations are independent, and that the number of cells with a value less than 5 is less than 20% of the total number of cells. If you're using the chi-squared test to evaluate a 2x2 contingency table, like we have shown for the epidemiology section in the first lecture, none of the cells can have a value less than 5. Now we will go through an example. Let's return to our example about wound infection. Both of the variables are categorical, whether antibiotics were given or not, and whether the patient had a wound infection or not. So we can use the chi-squared test to evaluate if there's a significant association between antibiotic use and, in this case, the cumulative incidence of wound infection over the study period. The formula to calculate the test statistic is written here. It is the sum of what you observed, your data, minus what you would expect to see if there were no association, this you have to calculate, squared, over that same calculated value of what you would expect to see. Like I mentioned, the expected value is what we would expect to see if there were no association. That is, if the null hypothesis were true. We can calculate this by multiplying the row total here times the column total divided by the grand total of patients in our study. So for A here, this is the people who got antibiotics and had a wound infection. We observed 16 people in this group. If there were no association between antibiotics and wound infection, we would expect to see 26, the total for that column, times 400, the total for that row, divided by the grand total of 500 patients. This gives us an expected value of 20.8. So observed 16 minus expected squared over the expected gives us 16 minus 20.8 squared divided by 20.8, or 0.144. We would continue doing this for each value in the table, then calculate the test statistic by adding them together. I would then compare this to a known chi-squared distribution for degrees of freedom of 1, where the degrees of freedom are calculated as the number of columns minus 1 times the number of rows minus 1. So 2 minus 1 times 2 minus 1 equals 1. Estimate my p-value. I would then compare this p-value to my pre-selected alpha, usually 0.05, as we've discussed before. If that p-value for my data is less than 0.05, I reject the null hypothesis and conclude there is a significant association between antibiotic use and wound infection. If it is greater than 0.05, I accept the null hypothesis that there is no significant difference between the proportions of infection among those who did or did not take antibiotics. Or in other words, that there is no statistically significant association between antibiotic use and risk of wound infection. Remember that the p-value alone does not tell me if this association is positive or negative. It does not tell me if using antibiotics is associated with a higher or lower risk of wound infection. For that, I have to calculate my point estimate and perhaps make a confidence interval. What point estimate would I calculate for this? I could calculate the cumulative incidence for those who were given antibiotics and not of wound infection, and then calculate something like a cumulative incidence ratio or a cumulative incidence difference, like we learned in lesson 1. So you might have felt a bit overwhelmed listening to those steps, which I completely understand, and calculating by hand can be a bit painful. This is why people often use computer programs to help them calculate their statistics. This here on this slide was done in Stata, but there are also other programs like R or SPSS or others you can use. My calculation says that the risk of wound infection in those exposed to antibiotics is 0.04, and the risk of wound infection in those who didn't receive antibiotics is 0.1. The software calculates the risk difference and risk ratio for you here, as well as the 95% confidence interval for each of these for you. And at the bottom, I see this chi-1 equals 5.84. This means that the chi-squared test statistic for 1 degree of freedom is equal to 5.84. And then I see this here telling me that the p-value is 0.0156. So given that p-value, should I accept or reject the null? I picked a critical value of 0.05, and 0.0156 is less than that. Therefore, I reject the null and conclude that there is significant association between treatment with antibiotics and the risk of infection. The relative risk is 0.4 and lies between 0.19 and 0.85 with 95% confidence. To a slightly different example. Suppose another hospital wants to do the same study on wound infection and how it relates to antibiotic use. However, they don't have as many patients at this hospital, and they're only able to record what happened to 200 patients instead of 500 like in the previous study. So here, is there a significant association between the use of antibiotics and infection risk? So in this example, the risks are the same, 0.04 here and 0.1 here for those who got antibiotics and who didn't. And therefore the risk ratio is the same, 0.4. However, the confidence interval now crosses 1. It ranges from 0.13 to 0.125 with 95% confidence. The fact that it crosses 1 is important because 1 is the point at which there is no association. There's no difference between exposed and unexposed. So anytime a 95% confidence interval crosses 1 for this ratio measure, or 0 for a difference measure, we know that there is not a significant association at the 0.05 level. This is confirmed with our p-value, which is now 0.1070, which is greater than our critical value of 0.05. So even though our point estimate, the risk ratio and risk differences that we can calculate are the same, the 95% confidence intervals and p-value indicate that there is not sufficient evidence to reject the null hypothesis. We conclude there is not a statistically significant association between antibiotic use and wound infection in this sample, even though we see that thus far a lower percentage of those treated with antibiotics get wound infections. And this is perhaps because I did not have enough power to, my sample size is not big enough to detect the difference between these two samples. Let's move on to Fisher's exact test. Like the chi-squared test, it's used to evaluate contingency tables when you have multiple categorical variables. It's called an exact test because the p-value is calculated exactly instead of being approximated from a known distribution of a test statistic like is done in the chi-squared test. It is used for smaller samples than you can use chi-squared for. Remember that we cannot use the chi-squared test if 20% or more of the boxes had a value less than 5, or if any of the boxes in a 2 by 2 table had a value less than 5. When this occurs, you can use Fisher's exact test instead. This test assumes that the samples are random and that observations, the individual patients in the study, in most of our cases, are independent. So I'm presenting here how you calculate Fisher's exact test by hand. However, you would really never do this. The probability of obtaining a certain set of values is shown here. Remember that a p-value is a probability that a result as extreme or more extreme than the one you observed would occur due to random chance alone. This just gives you the probability for a single kind of table, a single set of numbers. So this means you have to calculate the probability that every table that's as or more extreme as the one you observed would occur, and then add them up all together. And nobody wants to do that. So instead we use a computer. The most important thing is that you understand how to read the computer output. In this case, look up here in the upper right corner. I see that the risk ratio is 0.4 here. And the 95% confidence interval is 0.05 to 3.24. And here the p-value I can see is 0.3849. It's greater than my critical value, so I accept the null hypothesis and conclude there is no statistically significant association in this small sample. Now we will discuss tests to use for continuous data. The first question we have to ask ourselves is, can we assume a normal distribution? Because this affects the tests that we can use. So how can we determine if our data have an approximately normal distribution? Well, first, you could make a histogram and look by eye. Does this seem approximately normal? Like the histogram you see here on the right? You can look and see if the data are skewed, just push to one side, like we learned in lesson 1, or what the amount of kurtosis, how square or spiked the distribution is. You could also check to see if the 68, 95, 99.7% rule that we discussed the first week holds true. And you can also do a statistical test for normality, like the Shapiro-Wilk test. The null hypothesis here is that the data are normally distributed. So if p is less than 0.05, we reject the null and conclude that the data are not normal. If p is greater than 0.05, we accept the null and can proceed under the assumption that the data are normal. So this is results for two variables in that same data program. And I can see that this variable here is not normal, but that this one is. And this helps me choose what test I would use to look at both of these different kinds of variables. So now let's talk about the t-test. We use this test to compare the means of samples of continuous data. This assumes normality, and you don't need to know information about the values of the entire population like you do for some tests like the z-test. We won't discuss the z-test here, but you can look in the appendix if you'd like to learn more about it and see an example. As in the previous example, we calculate a test statistic and compare it to the known t-distribution for the degrees of freedom in your sample. So as n, the number in your sample, approaches infinity and the degrees of freedom get larger and larger, the t-distribution approaches the standard normal distribution, or the z-distribution, which again you can look at more in the appendix. There are a few different t-tests you can use. The first is the t-test for a single sample. You use this if you want to compare the mean of a sample to a known value. Another is the independent t-test. You use this to compare the means of two different groups. And there are different calculations you use if the variances of the samples are equal or not. And the paired t-test is used to compare the means of dependent samples. For example, for the same participant who has a value measured twice. These two measurements can't be considered independent since they were taken in the same person. So you use a special kind of t-test to compare those values. So let's start by discussing a bit more about the one sample t-test. when we compare the mean of our sample to a known value. My test statistic is calculated as seen here. X with the line over it here, X bar is the sample mean. Mu is the population mean, or the value I'm comparing to. S is the sample standard deviation, and N is the number of participants in my study. The degrees of freedom is N minus 1, or the number of participants or number of values in my data set minus 1. So let's go back to our height example. Let's say I have 100 women with an average height of 64 inches. The standard deviation of my sample is 2 inches. I want to know, is this significantly different from a known value of 63 inches? My null hypothesis is that my sample mean is equal to the known value of 63, and my alternative hypothesis is that it is not. So let's plug in our values to calculate the test statistic. 64 minus 63 over 2 divided by 10 equals 20. The threshold value for T with degrees of freedom 99 and an alpha of 0.05 is 1.98. Notice I have written here T sub 99, the degrees of freedom, comma 0.975. This is 1 minus alpha over 2, or 1 minus 0.025 when I chose the 0.05 for alpha. I have to divide alpha by 2 because I'm doing a two-tailed test, which is what we should almost always do. Because my calculated test statistic of 20 is greater than its threshold value of 1.98, I know that my p-value is less than 0.05. I therefore reject the null and conclude that my population is significantly different from the known value of 63. In the lower right-hand corner, I've done this using software. It tells me the probability of my mean not being equal to 63 is 0.0000. When it says this, when it's all these zeros, you can report that the p-value is less than 0.0001. Let's do the same test, but say I had only 10 participants. My critical value is now 64 minus 63 over 2 over the square root of 10, or 1.58. My degrees of freedom are now 9. And so the critical value for a t-distribution of 9, and then still using my critical value for a two-tailed t-test of 0.05, so 0.975 here, is 2.26. 1.58 is less than 2.26, so my p is greater than 0.05. I failed to reject the null. My sample is not significantly different from the population value. As before, on the lower right, you can see that I've had the computer do this for me and calculated a p-value of 0.1483 from my sample mean being different from 63, where this exclamation point before the equals means not equal to 63. These are for the one-tailed t-tests, where I'm only concerned about if it's less than the value or more than the value. But really, I just want to know what are the chances that it's different. So I almost always use this alternative hypothesis. Now let's talk about the independent t-test. This is used to compare two sample means from two independent groups. This is the test we needed to use for our original example comparing the heights of men to the heights of women. Why do we pick this? Because we know the sample mean and the sample variance. This is what we can calculate using our data, but we do not know the variance of the entire population. Therefore, we must use a t-test. To calculate this, we have to know the sample heights, the sample means, and the sample variances. So, which test do you do? This depends on the sample variances. You can do what's called an F-test to determine if the samples have equal or unequal variance, and the test statistic you calculate depends on this. I've written out the equations here, but please don't be too concerned with them because you almost will never calculate this by hand. Again, this is here for your information, but you will use a computer or other online resource to calculate these values. So let's do an example. Is there a difference in age standardized BMI between the US and Haiti? These are my values. Sorry. My null hypothesis is there is no difference in age standardized BMI between the US and Haiti. I have two samples here, each with 100 participants. And I know the sample means and the sample standard deviations. So are these standard deviations different? I'm doing the F test here. 2.1 squared divided by 1.9 squared equals 1.22. I compare this to the critical values for for F, when each group has 100 participants, and for an alpha of 0.05. 1.22 is between the critical values, so I accept the null and can proceed using the equation for equal variances. Note, if you use a computer program, you do not have to do this. The program will do it for you when you use the proper calculation, either equal or unequal variances, just depending on the values that you put in. So now I do my calculation, and again, I compare to the threshold value. And again, this is not something that you would normally have to do. I'm showing you this here, but really you would use the statistical software instead of calculating by hand. So let's look at an output from statistics software for this test. I told my software I want to do an independent t-test where the first group has 100 participants, mean of 25.3, and standard deviation of 2.1. And the second has n equals 100, mean 28.9, and standard deviation 1.9. It does the variance test for me and decides to proceed with a calculation for equal variances. At the bottom, I see here, null hypothesis is that there is no difference, that the difference is 0, and that the means are the same. It calculates for me various alternative hypotheses, the p-values associated with those various alternative hypotheses, depending on if I wanted to know the p-value for the one-tailed or two-tailed test. I want to use the two-tailed test here, as we almost always do. Therefore, the p-value is 0.0000 or less than 0.0001. I therefore reject the null and conclude there is a significant difference in BMI between Haiti and the US at the 0.05 significance level. The BMI in Haiti is significantly lower than that in the US, as I see here from my sample means. Now let's discuss the paired t-test. This is used for a couple things. First of all, repeated measures. For example, I'm interested in the blood pressure of a certain group of patients before and after the use of a medication. I measure their blood pressure before and after drug administration. These measurements I've made are no longer independent because I've measured them in the same person. I have to use a special form of the t-test to account for this lack of independence. It's also used for matched pairs. For example, instead of testing the same patient before and after medication administration, I give a placebo to one group and the medication to the other. I match these patients by age and sex between the groups to try to reduce bias. These matched pairs, through this matching, are no longer independent. So I use a t-test after to account for this, or the paired t-test rather. So the calculation is a little complicated, but basically, instead of examining the mean and standard deviation of each group, I look at the mean difference between the pairs, and the degrees of freedom are calculated using the number of pairs rather than the number of measurements. The null hypothesis is that the mean difference between the repeated measures or matched pairs is 0. Use your statistical software to calculate the p-value. In this case, I see that the p-value associated with the alternative hypothesis that the difference is not 0 is 0.0185, and it's less than 0.05. So I can reject the null and conclude that there was a significant change between the pairs from one test to the next. What if we want to compare more than two groups? We can use something called analysis of variance, or ANOVA, to compare the means of a number k of groups. The null hypothesis is that all the means are equal. The mechanism of the test is to compare the variability within groups to the variability between groups. I have listed here more information about how you calculate the within group and between group variance, but please consider this supplemental information. Usually you would use a computer program to calculate this. Basically, what's important to understand is that when we're comparing the within group variance to the between group variance, if the within group variance is of a similar size or greater than the between group variance, it's likely that there is no difference between these groups, that they came from the same overall population. If the within group variance is much less than the between group variance, then it is likely that they are, in fact, different. And this is what the ANOVA calculation does. So let's do an example. I want to know how systolic blood pressure compares between three groups by race: Black, white, and other. My null hypothesis is that the systolic blood pressure in all three groups is the same. I do the ANOVA calculation and get a p-value of 0.0008. I reject the null and conclude that the mean systolic blood pressures are not all the same. But what do I do now? I know they're not the same, but how do I compare each of them? I have to compare the pairs with t-tests if I want to know how if each group varies significantly from each other group. Also, remember again, the p-value is the probability that a value as extreme or more extreme than the one I observed would be obtained from chance alone. Let's say we did 20 tests. If in each test there's a 5% chance that I would see this occurring due to chance alone, after I did 20 tests, I would likely get a significant result even if there were no association, simply because there's a 5% chance each time. So when I test the data multiple times, I need to adjust the p-value to account for this. You can either adjust the p-value or you can adjust the critical value and compare your set p-value to that new critical value. So there are different ways to correct, but one of the most common is called the Bonferroni correction. And to do this, we just divide, in this case, the critical value by the total number of tests performed. To compare three groups, I have to do three comparisons: one with two, one with three, and two with three. So I need to divide by three. The new critical value is 0.05 divided by 3, or 0.0167. The p-value has to be less than 0.0167 for each of these t-tests in order for me to reject the null. And you can do this all in a single calculation using statistical software. You can do the ANOVA and then follow it up with those t-tests with the corrected adjusted p-values. So there are different types of ANOVA you can do. There's the one-way repeated measures ANOVA, which compares means when the same patients are tested multiple times. For example, I want to know if a certain drug has an effect on blood pressure. I test the same patients at time 0, at 1 month, and at 2 months. Factorial ANOVA. This compares means across multiple categories and assesses interactions between the categories. For example, I want to know if systolic blood pressure varies by race and gender. The effects of race and gender may be independent, or they may interact. That is, the effect of one depends on the level of the other. So this is similar to that concept of effect modification that we talked about in the first lecture. And then there's MANOVA, which analyzes multiple groups of means, multiple dependent variables across a category. I've put an example of factorial ANOVA into the appendix, but we won't go over it here. So we've talked about tests to use for 2x2 tables and for tests to compare means of groups. Now, what if we want to compare two continuous variables? We can use the Pearson correlation. This quantifies the degree to which two continuous variables are associated. It assumes a linear relationship between the two variables, and you can visualize this with a scatter plot. If the relationship isn't linear, you can transform your data to make them more linear. For example, instead of comparing x to y, you can compare x to log y, or square root of y, or y squared, whatever you choose to make your data more linear. However, note that this will make your results more difficult to interpret. R is the Pearson correlation coefficient. The strength of the relationship increases as the absolute value of R approaches 1. When R is less than 0, there is a negative correlation, a negative slope. When R is greater than 0, there is a positive correlation, positive slope. So this has a very strong correlation that is negative. This has a very strong correlation that is positive. Now let's move on to non-parametric methods. So what do we do if the data are ordinal in their ordered categories? What do we do if we have continuous data, but they're not normally distributed? What do we do if the size of our sample is really small, so we can't rely on the fact that sample means come from an underlying normal distribution? That is the central limit theorem, which you can look into more on your own if you're interested. but it's a reason why we can choose certain tests when our sample sizes are big enough. And you can see that in the map on the first page that helps you choose your test as well. So we have to use another type of test that does not rely on us knowing the underlying distribution of the data. Because we don't need to know the parameters of this distribution in order to use these tests, they are called non-parametric. The Mann-Whitney test is a non-parametric test used to compare two groups or conditions, and it's analogous to the two-sample independent t-test. Each subject has a score, and they're ranked. And the Mann-Whitney test determines if there is a statistically significant difference between these two groups based on these rankings. It assumes that the dependent variable is ordinal or continuous, but the independent variable is the two groups, or categorical groups, and that the groups are not normally distributed. An example of when to use this would be the following. Let's say a new medication is developed to treat postoperative pain. We want to know if using this medication significantly lowers the use of opioid medication. So group 1 is given opioids alone, and group 2 is given opioids plus the new medication. So that's the independent variable, which group they're assigned to. And the dependent variable is the number of doses of opioids taken during 1 week post-op. So here's a bar graph of the number of opioid doses taken by patients in each group, if they were given just the opioid alone to manage their pain, or if they were also given the new drug. Because they're counts, they aren't continuous values. Therefore, we can't use a t-test to compare the means. If the data were continuous, what would we need to check before using a t-test? That they were approximately normal. For example, the Shapiro-Wilk test. The calculation is difficult to do by hand because there are quite a few steps, and so it's better to use statistical software. And you can see this is what the output would look like, and we can look at this probability here. If one of the sample sizes is less than 10, we have to use this exact probability versus this probability that's based on an underlying distribution here. So the Wilcoxon-signed rank test is analogous to the paired t-test, and similarly to the paired t-test is used for repeated measures or matched pairs. Like the Mann-Whitney, we use this for ordinal or continuous dependent variables to compare groups that aren't normally distributed. So here's an example of when you would use the Wilcoxon-signed rank test. Does music in the OR affect the surgeon's mood? Condition A being no music, condition B, music. So each person in our sample is the same surgeon tested in two different conditions. So these aren't independent measurements. So we have to use a paired test. Because the dependent outcome measure is a score from 1 to 10, this is an ordinal measure, and so we can't use tests that require normality. Like the Mann-Whitney test, the calculation is pretty complicated to do by hand, so statistical software is used. Like always, we compare the p-value to the pre-chosen critical value to decide whether or not we will accept or reject the null. In this case, the null being that the surgeon's mood is the same in both conditions. So there are rules about when you can use this probability here versus the exact probability, and you can read more about that here. And note that these really aren't used too often. Most of the time, we will end up using those tests for the parametric tests like the t-tests or ANOVA or other tests which assume normality. But it's really good to be able to know and recognize what these tests are as well. So the Kruskal-Wallis test is analogous to the ANOVA. We use it when we are comparing 3 or more groups of different subjects, where the measure we're interested in is not normal and each subject produces a score. We are testing if there's a significant difference between the 3 or more groups, where the null hypothesis is that each is the same. And you have to use this done procedure afterwards to compare specific groups if you would like to do so. So here's an example in which we'd use the Kruskal-Wallis test. Is there a difference between patient assessment of back pain between the 3 different medication groups, A, B, and C, where back pain is assessed as a score from 1 to 10? Finally, let's discuss the Spearman correlation, which is analogous to the Pearson correlation. This can be used when two variables are not normally distributed, or there are outlying values in the data, or when one of the two variables is ordinal rather than continuous. We use classes of x and y rather than values of x and y to calculate this Spearman coefficient. Now, let's discuss regression. These are analyses used to quantify the association between an outcome variable and one or more risk factors or confounding variables, and can also be used to create a model that can predict the value of the dependent or your outcome variable if the values of the independent variables that we insert into our equation are known. So the type of regression you use depends on the outcome variable. You use linear regression if your outcome variable is continuous, logistic if it's categorical. Really, it's logistic is used for binary, but there are certain kinds of logistic regression you can use for categorical variables when there are more than two groups. Poisson regression is used for discrete numeric or count outcome variables, and the Cox proportional hazards model is used for time to event. So, linear regression. This allows us to estimate the linear relationship between a dependent variable, our outcome variable, and one or more independent variables, and can be used to predict the value of the dependent variable when the values of the independent variables are known. Note this doesn't imply causality, just the association. It assumes independence, that those outcome variables are independent, outcome values are independent, linearity, that the relationship between x and the mean of y is linear, normality, that for each x, y has a normal distribution, and that the residuals, the differences between the observed and predicted values, are normally distributed, and homoscedasticity, that variance is equal across all the variables. And there are tools that you can use to check on each of these assumptions to make sure that you can proceed with your linear regression. So linear regression with a single independent variable. Unlike correlation, this predicts the change in y with a given change in x. So our result is in the form y is equal to beta naught plus beta 1 times this x if we have a single independent variable plus the error term. So each 1 unit increase in x has a beta 1 unit increase on y. And note that beta 1 is related to that Pearson coefficient. So our null hypothesis in the case of a simple linear regression is that this beta 1 term, or the slope that you see here of this line, is equal to 0. If p is less than 0.05, we can reject the null and conclude that x has a significant effect on y, and that this linear line here has a good fit. We can also test the fit of our model using r squared, the square of the Pearson coefficient, and this corresponds to the proportion of variability of y explained by the model, by our x. Multiple regression is when you have multiple x terms, multiple independent variables, each of which have a beta coefficient here that determines what impact they have on the value of y. Each x can be continuous, categorical, whatever you like. We choose the type of regression based on the data type of this outcome measure, not the predictors. Although if it's categorical, we need to use a dummy variable. For example, we could say that x2 equals 1 when race equals white, and x3 equals 1 when race equals other, for example. This is similar to the factorial ANOVA that we discussed a little bit earlier. So using multiple linear regression, we can determine the effect of multiple explanatory variables, these different x's, on our dependent variable y. Each beta takes into account the effect of the other variables. That is, they are adjusted for the effects of the other variables. And each beta is the increase in y with a 1 unit increase in x, given that all the other x's are held constant. We examine the fit of the model using an r squared or adjusted r squared that takes into account the complexity of the model. So how do you build a model? We want to include explanatory variables and confounders, but not collinear variables. Recall that confounders explain some variation in y and can lead to incorrect estimates if not taken into account, whereas collinear variables do not independently predict the outcome because and can lead to increased standard errors, increasing their risk of type 2 errors. You can also include things like interaction terms to check for effect modification. And there's many ways to do this. And this is um, a bit complicated, but I just wanted to give an introduction now because you will often see regression models used in many papers, and you might want to do this for your own topics in the future. The best way to build a model is based on science. You believe ahead of time that certain things are likely to have an effect. For example, that prior research tells you that age and smoking status is associated with blood pressure, so you decide to include those. There are other methods of model building, but these are beyond the scope of this course. All have benefits and issues. Things like doing a univariate screen, so screening each of your potential independent variables to see if they're associated with your outcome variable. To use every available variable you have, to do some sort of automated selection technique, which these are examples: backward elimination, forward selection, stepwise selection. You can use models based on the change in that beta coefficient, models based on the change in something called AIC, and something called purposeful selection. These are all options you can use that you can read more about if you decide to dig deeper into regression and model building. So just a little bit more about the other types of regression. Logistic regression is used when the outcome variable is dichotomous, when it's binary. You can also do something called multinomial logistic regression when you have a categorical variable with more than two groups. The reasons to use are to identify factors that are associated with the probability of a certain event, and to create a model that a given person will undergo an event if certain characteristics, those values of predictor variables, are known. The mean of the outcome y is the proportion of the time that y equals 1. What does beta mean? For each 1 unit increase in x, the log odds of the outcome changes by beta. That's a bit confusing to think about. So outcomes are usually presented as odds ratios because the probability might change with the value of x, but the odds stay the same. And remember, we talked about odds ratios in that first week if you want to review what an odds ratio is. Poisson regression is used for count data. Why would we use this? For example, we want to predict the number of times that a certain event will occur given certain values of predictor variables. And what does beta mean? For a 1 unit increase in x, the log of the count changes by beta. Also in our first lecture, we discussed the Kaplan-Meier estimator. And we made survival curves based on data that we had. So how do you know if two survival curves are different? You can do something called a log rank test, which tests if distributions of survival time are identical, but can't evaluate the effects of more than one risk factor at a time, and can't be used to determine the relationship between how long somebody survives and any risk factor that's continuous. If you want to be able to account for multiple predictors at the same time, multiple variables at the same time, or any continuous variable, we need the Cox proportional hazards model. Predictors can be categorical or continuous, but it relies on something called the hazard being proportional, where the hazard is the instantaneous rate of the event. And we interpret an adjusted hazard ratio to determine how each predictor variable affects the survival curve. So this is the end of the lecture today. We have an appendix that follows that has information on several other tests we have not covered more in depth in this course, but if you're interested, you can look at more information on. And again, I want to say that this is not something that can be learned overnight, and these are difficult topics that take a lot of time to get comfortable with. You have now just started that process, and some of you may have started it already, and we'll continue with example problems, but please don't feel discouraged if you don't get it right away. The goal is just to have an introduction to these topics, to start understanding the language that statisticians speak with and the language that is used in papers that you will read, to have a better concept of what things reported in papers mean, and to have a general idea of what kind of analyses you might want to pursue for your own projects. And then you can talk to with your mentors or others with more experience in statistics and gain their help as you continue to learn about these topics. So thank you all for being here, and see you at office hours.